So water dissolves both polar molecules and ions. And by polar molecules, we mean molecules that might not be fully charged like an ion is, but still has some partial charge to it. Now, water organizes nonpolar molecules. Water doesn't dissolve nonpolar molecules. Water dissolves polar molecules and ions with charges or polarity to them. But nonpolar molecules are organized by water in a very particular way. And we refer to the nonpolar and polar molecules as hydrophilic or hydrophobic. Hydrophilic molecules are polar or ions. That is, they have some charge distribution on them. And those molecules love water and will dissolve easily in it. But hydrophobic molecules are water-fearing. Hydro-water-phobic fearing. And because hydrophobic molecules are nonpolar, water causes the hydrophobic molecules to separate from the water. So you all know that oil slicks float on water. They don't mix with the water well. Oil and vinegar is another good example. The nonpolar oil does not mix well with the polar vinegar, which is basically a water-based liquid. So water causes hydrophobic molecules that are nonpolar to aggregate or assume specific shapes. And that becomes very, very important when we talk about protein structure. So keep that in mind. Hydrophobic molecules are nonpolar, they don't like water, and they separate from water. Water kind of organizes them, keeps them away from mixing with water because they are nonpolar. Now, a sixth feature of water that's important is that water can form ions. What we mean by water being able to form ions, or the ionization of water, is that H2O can dissociate to hydroxyl anions plus hydrogen ions that are positively charged. These are anions, and this is the cation. And so in any volume of water, a certain percentage of the H2O molecules will be dissociated into the hydroxyl ion and the hydrogen ion. So in pure water, if we have pure water, we can define the hydrogen ion concentration formed when molecular water dissociates into the hydroxide ion and the hydrogen ion. In pure water, the concentration of hydrogen ions is 10 to the minus 7th moles per liter. A mole is Avogadro's number of atoms, and Avogadro's number is 6.022 times 10 to the 23rd, a large, very large, almost astronomically large number. So in pure water, the concentration of hydrogen ions is 10 to the minus 7th moles per liter. And we consider that to be neutral, neither acidic nor basic. And now we need to talk about the definition of pH. So pH is the negative logarithm of the hydrogen ion concentration. So the negative logarithm of 10 to the minus 7th is 7, and that is the pH of pure water, which is neutral. So we'll define a pH of 7 as neutral. So pH equal to 7 implies neutral, neither acidic nor basic. So then acids and bases dissociate in water in the following way. That any substance that dissociates in water that will donate hydrogen ions to solution, that will increase the hydrogen ion concentration in the aqueous water solution. But because pH is the negative logarithm of the hydrogen ion concentration, that will lower the pH. As the hydrogen ion concentration gets higher, the pH gets lower because pH is the negative logarithm of the hydrogen ion concentration. So for example, if in a given solution of water, in a beaker of water, there is a molecule is dissolved in there which adds hydrogen ion concentrations to to the solution. It dissociates and produces hydrogen ion concentrations. Let's say that the hydrogen ion concentration then becomes 10 to the minus fifth, a much higher concentration than 10 to the minus seventh. The pH of that solution would be 5, the negative logarithm of the hydrogen ion concentration. So the higher the hydrogen ion concentration, the lower the pH. And for acids that dissociate in water and that donate hydrogen ions to solution in water, the more hydrogen ions it produces, it makes it a stronger acid. So a strong acid lowers the pH by donating more hydrogen ions to solution than a weaker acid does. And a base is just the opposite. It's excuse me. It's a substance that removes hydrogen ions from solution from an aqueous water solution. So it accepts hydrogen ions from the aqueous solution and therefore lowers the hydrogen ion concentration. So imagine that you had a beaker of water now, and you dissolve and you mix in a base. A base will take hydrogen ions out of solution. It'll lower the hydrogen ion concentration because it will grab those hydrogen ions and hold them. That's what a base does. It accepts hydrogen ions from the aqueous solution. Therefore, it lowers the pH. It lowers the hydrogen ion concentration, I should say. So let's say the hydrogen ion concentration in this basic solution here is hydrogen ion concentration is something like 10 to the minus eighth. Well, then the pH of that solution then, if that's moles per liter, then the negative logarithm of that, it would be 8. Therefore, a base, by lowering the hydrogen ion concentration, 10 to the minus 8th is lower than 10 to the minus 7th, a base lowers the hydrogen ion concentration and therefore raises pH. So we can look at the pHs of various solutions in water. Let's look at pure water. It has a pH of 7, as we've already said, because the concentration of hydrogen ion concentrations is 10 to the minus 7th moles per liter. Going to the acidic side of things, let's look at your stomach acid. It has a pH of 2. It's extremely acidic. And the enzymes that digest food in the stomach need to be very resistant to that high acid concentration. Tomatoes are pretty acidic, pH of 4. Hydrochloric acid, a very strong acid, pH of 1. Going to the basic side of things, seawater has a pH of about 8 because there are dissolved substances in seawater that remove hydrogen ions from the water solution. Baking soda, pH 9. The Great Salt Lake in Utah has a pH of 10. It's very alkaline. Ammonia, very alkaline solution. Ammonia it accepts hydrogen ions by having nitrogen bind to those hydrogen ions, form bonds with them. pH 11. Bleach, sodium hydroxide, very strong base, has a pH of 14. Now, buffers are an important concept in biology. And a buffer is something that, when dissolved in water, can cause the pH to be resistant to large changes. And a buffer can release hydrogen ions if you add a base to the solution. So a base, if you add a base to the solution, that will a buffer will release hydrogen ions if a base is added. So let's say you have a solution of water here in a beaker, or in a cell for that matter. Imagine you have an aqueous solution in a cell. Let's say that in your aqueous solution you now add a base. What will that base do? That base will remove hydrogen ions from solution. Well, at a buffer, if that is dissolved in this water, when that happens, as hydrogen ions are removed by the base, the buffer will release hydrogen ions in a compensatory manner, so that there's no large-scale change in the concentration of hydrogen ions, and therefore no large-scale change in pH. But a buffer will absorb hydrogen ions if an acid is added. So instead of adding a base, if you have an acid in here, you add an acid to the solution, but there's a buffer in here, the buffer will accept the hydrogen ions that the acid will donate to solution. So a buffer then does exactly what its name implies. It buffers the aqueous solution from large-scale changes in pH, keeping the hydrogen ion concentration relatively constant. And for example, we can look at the action of a buffer here, and this is the buffering range between pH, let's say, 4 and 6. So we're adding different amounts of base here, increasing amounts of base along the x-axis, and we're measuring pH along the y-axis. Well, out of the buffering range, pH will increase rapidly as base is added. But in the buffering range, we have almost a 5-fold increase in the concentration of base. And if there weren't a buffer in solution, then we would keep along this trajectory, the initial trajectory, pH would rise very rapidly. But the buffer in solution is able to donate hydrogen ions to solution as the base is removing them from solution, so that the pH change from 1x concentration of base to 5 times that concentration, essentially, the pH change is very small. It's only 2 pH units, where it would be a much quicker change if there weren't a buffer there. So in biological systems, buffers can usually consist of a pair of molecules, and we can consider that for carbonic acid, which forms as a result of the dissolution of carbon dioxide in water, in our blood, really. So let's talk about that right now. If we consider then carbon dioxide dissolving in water, and our blood is water, and carbon dioxide dissolves actually in blood, and our blood is buffered by the action of the carbonic acid, which forms as carbon dioxide, carbon, 2 oxygens, carbon dioxide, double bonds here. As carbon dioxide dissolves in water, it forms carbonic acid. But carbonic acid can dissociate to produce hydrogen ions and bicarbonate. So carbonic acid is the buffer, and if bases are added, which donate hydrogen ions to solution, carbonic acid can accept those hydrogen ions that a base is, if a base is added, thereby removing hydrogen ions from solution, carbonic acid can donate hydrogen ions, which will compensate for that base being added. If, on the other hand, an acid is added, which is donating hydrogen ions, increasing the hydrogen ion concentration, carbonic acid can accept those hydrogens and yield water and carbon dioxide. So carbonic acid is able to buffer our blood. Now we can move on to chemical reactions and just point out that they involve the formation or breakage of chemical bonds, and that in chemical reactions we have reactants and products. And atoms can be shifted from one molecule to another in a chemical reaction. Chemical reactions are influenced by temperature, the concentration of the reactants and the products, and catalysts, very importantly. We will see that biochemical reactions depend upon protein catalysts, enzymes in other words, to allow biochemical reactions to proceed at a reasonable biological pace. And many actions, as I pointed out, are reversible. So that ends our introductory chemistry lecture, and now we can move on to biomolecules.